Let's jump into one of the greatest detective stories in the history of science, the incredible journey to understand the atom. For thousands of years, it was just an idea, a ghost. But then, in a little over a century, scientists went from proving it was real to literally smashing it wide open.
And that brings us to the central mystery, doesn't it? The word atom actually comes from the Greek word for uncuttable. So if they were supposed to be the smallest, most fundamental things in the universe, how in the world did we figure out how to cut them? How do you even begin to look inside something that by its very definition you can't break apart? Well, that is the puzzle we are about to solve together.
So where does this story even begin? Well, you might be surprised. It doesn't start with physicists and particle accelerators, but in the labs of chemists, way back in the early 19th century. They were the ones who found the first pieces of hard evidence that the atom wasn't just a philosophical idea, it was something real, something you could actually measure.
Right, so the main character here was a guy named John Dalton, and he noticed this really interesting pattern. When elements combine to make compounds, they always do it in fixed ratios by weight. So, for instance, you could take 28 grams of nitrogen, and it might combine with 16 grams of oxygen, but then in a different compound, that same 28 grams of nitrogen would combine with exactly double the oxygen, 32 grams. The only way this simple whole number pattern made any sense, Dalton thought, was if matter was made of these fundamental, unbreakable little blocks, and he called them atoms.
But this created a massive new problem. Chemistry could tell you the weight ratios, sure, but it couldn't tell you how many atoms were involved. Just look at water. They knew it was 8 parts oxygen to 1 part hydrogen by weight. Okay, fine. But does that mean the formula is HO and an oxygen atom is just 8 times heavier than hydrogen? Or is the formula H2O, which would mean oxygen is actually 16 times heavier? There was no way to know for sure, and this question stumped chemists for decades.
And the solution, believe it or not, didn't come from chemistry at all. It came from physics. Avogadro came up with this brilliant, simple idea. If you have equal volumes of any gas at the same temperature and pressure, they will always have the same number of molecules. Now, since experiments showed that it takes 2 volumes of hydrogen gas to fully react with 1 volume of oxygen, the logic was crystal clear. The water molecule must have twice as many hydrogen atoms. The formula had to be H2O. And just like that, the whole puzzle of atomic weights was unlocked.
All right, so for a while there, the atom seemed solid. It seemed predictable, indivisible, pretty much figured out. But a whole new field of science was bubbling up, all about the weird, mysterious force of electricity, and it was about to blow that whole picture wide open. So scientists started messing around with these glass tubes with all the air sucked out of them. They'd pass a high-voltage current through, and they saw these strange, eerie rays streaming from the negative end, the cathode. These cathode rays would make the glass at the other end glow. But what on earth were they? Some weird kind of light? Or something completely new?
So they started running tests, and what they found was just bizarre. These rays could actually push a tiny little paddle wheel, so they had some kind of physical substance. They carried a negative electric charge. They could be bent by magnets, and they could be bent by electric fields. The conclusion was pretty much unavoidable. These were not waves. This was a stream of actual, physical, tiny little particles. And they got a name: electrons. Now here's the real kicker. By measuring exactly how much the rays bent, scientists could actually calculate the mass of these new particles. And the result was absolutely mind-blowing. They were almost 2,000 times lighter than a single hydrogen atom, which up until then was the lightest thing anyone had ever even imagined. And that was it. That was the moment. For the first time, science had definitive proof that a piece of matter smaller than an atom existed. The atom, the uncuttable, was not uncuttable after all. It had parts. Okay, so the discovery of the electron just opened up a whole new can of worms. If atoms have these tiny negative particles inside, there must be something positive in there too, right, to balance it out? But an even crazier mystery was about to appear. What could actually make an atom just fall apart? The next clue came from a place nobody expected. Researchers like the legendary Marie Curie discovered that some elements, like radium, were doing something that should have been impossible. They were just spontaneously pouring out incredible amounts of energy, all by themselves. And when this radiation was passed through a magnetic field, it split into 3 distinct types: positively charged alpha rays, negatively charged beta rays, which turned out to be just super fast electrons, and gamma rays, which had no charge at all.
So in 1902, Ernest Rutherford and Frederick-Soddy came up with this completely radical theory. They said radioactivity isn't a chemical thing, it's the atom itself, spontaneously disintegrating. An atom of one element was literally transforming into an atom of a completely different element, and it was releasing a truly enormous amount of energy in the process. Atoms weren't just divisible, they were complex, powerful little machines.
So now, the pieces of the puzzle were finally starting to come together. We know atoms have tiny negative electrons. We know they can spit out these bigger positive alpha particles. The race was now on to figure out how all these parts were arranged. I mean, what does an atom actually look like on the inside? A huge clue came from this brilliant invention called a cloud chamber, which let you see the actual paths these alpha particles took as they flew through the air. And what they saw was fascinating. Most of the particles zipped along in perfectly straight lines. But every now and then, one would just, bam, it would make this incredibly sharp turn, a sudden kink in its path, as if it had bounced off something tiny but incredibly solid. And this is the question that just obsessed Rutherford. Think about it. An alpha particle is heavy, and it's moving at a blistering speed. To knock something like that so violently off course would take an absolutely immense repulsive force, all concentrated in one tiny little spot inside the atom. What in the world could it be?
Well, Rutherford did the math, and he realized there was only one possible answer. To get that kind of deflection, all of the atom's positive charge and almost all of its mass had to be crammed into an unbelievably tiny, dense little core at the very center. He called it the nucleus. And the electrons? They were orbiting this nucleus from a huge distance, meaning the atom itself was almost entirely empty space. The scale here is just staggering. If an atom were the size of the entire planet Earth, its nucleus would be just a tiny dot.
So there you have it, this beautiful, elegant picture of a miniature solar system. It perfectly explained all the experimental results, but there was just one catastrophic problem. According to all the known laws of physics at the time, this atom could not possibly exist.
Yeah, the model had two fatal flaws. First, what's called the death spiral. Classical physics was very clear. An orbiting charged particle like an electron must constantly radiate energy. And if it's losing energy, it has to slow down and spiral into the nucleus in a split second. Atoms should just instantly collapse. The second issue was an identity crisis. This model allowed electrons to have any old orbit they wanted, which would mean no two atoms of, say, gold would be exactly alike. But we know from looking at the light they emit that every single gold atom is a perfect identical copy of every other one. And this is where we have to leave the story, right on the edge of a cliff. The experimental evidence pointed directly to a nuclear atom, but the fundamental laws of physics said that atom couldn't last for a fraction of a second. It was a brilliant success and a complete failure, all at once. Science had hit a dead end, and breaking through this paradox was going to require a revolution so profound it would shatter our entire understanding of reality itself.